The second lecture in this set is going to introduce you to the ideas of prior distributions, data models, and posterior distributions, which are sort of the heart of what a Bayesian statistician looks at. So we already contrasted the Bayesian approach to statistics with the frequentist approach to statistics. And in this lecture, I'm going to give you a little bit more depth on what the Bayesian method entails. The core pieces of Bayesian inference are the prior distribution, the data model, and the posterior distribution. The way I will write these is using theta as my generic parameter and x as my generic data. I'll write the prior distribution as p of theta. Now, in the past, we've used f as our letter for distribution functions, for PDFs, PMFs. Here I'm using p, and this will be a little clearer when I discuss conjugacy in a little bit. But for now, just stick with me. Prior distribution is going to be a function p of theta, which is a PDF. My data model is going to be f of x given theta. So x is the data I get to see, and my distribution for the data x is something that depends on my parameter theta. So I have prior beliefs about my parameter theta, I have some data, and those data depend on the parameter theta. And then my posterior distribution is going to be p of theta given x. So this is my beliefs about theta after I've seen the data x. Like I said, these are the three core pieces of Bayesian inference, of Bayesian statistics. So let's take them one by one. So the prior distribution reflects your beliefs about the parameter theta prior to seeing any data. Now, because this isn't a Bayes class, I'm not going to talk too much about different choices of prior that we could pick, other than to say that I can do this a few different ways. I can do an informative prior, a prior that incorporates knowledge I have from outside the problem. I can also do something that I often call a reference prior, which is to try to contribute as little information as possible to my analysis here and let the data basically speak for itself. There are advantages to doing either of these, which, like I said, I'm not going to talk about much in this class. I save that for my Bayes class. This is a long discussion about priors that I could have. But so the prior distribution is a reflection of my beliefs about parameter theta prior to seeing any data. Let's talk about an example here. So in the previous lecture, I mentioned student heights. So let's let theta be the average height for the population of UNM students. And so obviously, if I'm going to look at a bunch of UNM students, if that's going to be my data X, then their height should depend on the average height for the population of UNM students. So if I want to talk about my prior beliefs about that height, well, what might I say? I don't know exactly what the average height for the population of UNM students is, but I'm going to guess that it's going to be somewhere between 5 feet and 6.5 feet. It would be pretty strange if the average height for all UNM students was any less than 5 feet or any greater than 6.5 feet. And so I'd be pretty comfortable saying that I believe that it lives in that range. An example of that, I could do a uniform. Now let's put this in terms of inches. A uniform 5 feet is 60 inches, 60, and 6.5 feet is 78 inches. Oh, I can write that a little better. Let me clean this up a bit. So somewhere between 60 inches and 78 inches. I could say that this could work for, I'm going to watch me edit. The downside to online lectures is that just like in-person lectures, every once in a while I write something a way that isn't quite how I'd like to write it, and I have to spend time fixing it. So what I can do is I can say, let's connect up my terminology here. P of theta is, no, I want to do it even slightly different than that. I want to say theta is distributed uniform 60, 78. So my prior belief about theta is that it's got to live somewhere between 60 and 78 inches. I'm not saying that I think any value in there happens to be more or less likely. I'm just saying that I think it's got to be there and they're all about equally likely. Now that's not a great prior belief, but it should work. I don't think that the average height of UNM students could be anywhere outside of that. So if this is my statement about my prior belief, I can write that P of theta is equal to, now how do I write the PDF of the continuous uniform distribution? This is going to be 1 over 78 minus 60 is 18 times the indicator function, 60 to 78, of theta. So remember, my indicator function says that if theta is inside the interval from 60 to 78, the indicator function will be 1. If theta is outside the interval from 60 to 78, if theta is 59, if theta is 80, then the indicator function is going to be 0. And so if I plot this thing, I'm going to have 60, 78. I'm going to have just a flat graph between 60 and 78, and then it's going to be 0 everywhere outside that. And how high up is this getting? It's getting up to 1/18. And if I take the integral from 60 to 78 of 1/18, well, the integral, I mean, this is just a rectangle, right? And so it's a rectangle with length 18 and height 1/18, which means when I multiply length by height, the area of this rectangle is 1. So my probability adds up to 1. This is what I want. Okay, so this is my prior belief about student heights. Like I said, this isn't necessarily a particularly good prior belief, but I just want to give you an example of what sort of distribution I can use here. Now, obviously, I could consider a distribution that's more like that's supposed to be normal-ish, a bell curve, that peaks around some value in the middle here, like let's say 68, because I have to include both men and women, and so the average height for everybody at UNM, both men and women included, might be about 68 inches, 67 inches. I don't know, but it could be something in there. It's more likely it's going to be somewhere in the middle instead of flat on 5 feet to 6.5 feet. That seems unlikely. But both of these are valid, and it's easy for me to write the uniform distribution here. So that's why I'm using the uniform distribution. Now, my prior distribution, like I said, doesn't have to be particularly good. I'd like it to not be awful. I'd like it to at least kind of reflect my data. But the issue is I don't have any data yet. So this is just prior beliefs. Now I'm going to collect some data, bring in the data, and then use the data and my prior beliefs, combine those guys up to get my posterior beliefs, which says a lot more about what's going on. If that's the prior, our next piece is the data model. Now again, I'm being a little overly simplistic here, so I'm going to state a data model for these data that I don't think actually holds, and I'll explain to you why I think that that's the case. But so what do we often have for a data model? We might have something like the height x of a particular student is normally distributed with some mean theta and some variance, and so that I don't have a lot of free parameters floating around in here, let's just fix a variance or a standard deviation. So what do I think is a reasonable range of heights for people? Standard deviation on heights is probably, if I'm including men and women, let's do 3.5 inches. So I'm putting the squared on there because I want this to be a variance term. So my heights are normal with mean theta, my unknown parameter, and standard deviation 3.5. Now, like I said, I don't think this is a particularly good model. Why not? Because I didn't limit my population here. I said all students. If I'd limited my populations to male students or female students, then each of those subpopulations tends to be pretty much a normal distribution for heights. When I combine them up, it's a mixture of two normal distributions, and it's going to look a little bit more complicated. It might be bimodal. I'll probably erase this in a second, but so it could be something that looks like that. It's more likely that they'd sort of combine up and give you a really weird lumpy shape, where the peaks happen kind of together, but not quite at the same point. So anyway, just a simplistic example here, so I'm going to use a normal distribution. So this is my data model, and now I'm going to need to convert this data model. I need to convert the data model from a function of the data which will usually be a PDF or a PMF, to a function of the parameter. And we've talked about this before. That's what we call the likelihood. And the way we get the likelihood out of the PDF is it's just the same. You write all the same terms. It's just the likelihood is now a function of the parameter instead of the data. So for example, if I've got this data model for x, then f of x given theta would be, okay, so that's my variance term. So I need 1 over square root of 2 pi 3.5 squared times e to the minus 1/2 x minus theta over 3.5 squared. So that's my PDF for x given theta. So what's my likelihood for theta given x? Well, it is exactly the same function. Except now it's a function of theta instead of a function of x. And usually I'll have a random sample, and so I'll be taking a bunch of these, assuming that my random sample is a bunch of independent observations. I'll be taking a bunch of these PDF guys, multiplying them all together, and then that multiplied version is going to be the joint distribution, the joint PDF for all of the x's. And then my likelihood for theta given all of the x's is again going to be the same thing. So it's just going to be all of the individual guys multiplied up. So this is our data model. Okay, what do we do once we have both our data model and our prior? At this point, we move to the posterior. Posterior distribution. So the reason that Bayesian inference has the name Bayesian is that it goes back to Bayes' theorem. Let's consider Bayes' theorem again real quick, and we'll build in towards how we get this posterior distribution thing. So recall that for two events A and B, Bayes' theorem says probability of B given A is equal to, well, we know from basic probability that this is the probability of A and B over the probability of the thing we know, the thing we condition on, probability of A. Bayes' theorem expands that out and says, well, what is the probability of A? I can break that up into the B is true piece and the B is false piece. So probability of, yes, probability of A given B, probability of B plus probability of A given not B, probability of not B. And by the law of total probability, the sum of these two, so this guy, this is just the joint probability of A and B. This is just the joint probability of A and not B. If I add those together, either B or not B has to happen. So by the law of total probability, this is going to be the probability of A. And then up here, probability of A and B, well, that's just this guy that I had here. Probability of A and B is the same thing as the probability that B happens, and then the probability that A happens when we already know that B happened. Okay, so now that we have Bayes' theorem back, let's take a look at the formula for the posterior distribution. For the posterior distribution of our parameter theta. So P of theta given x is going to be equal to P of theta, our prior, times L of theta given x, what our data model says about our parameter theta. So we've seen x. Often we'll write this a different way. I like to be careful with likelihood and not likelihood, but you will often see this written f of x given theta, because they're basically the same thing. So if I think about this, what do I have? I mean, this really seems to match up pretty well with what we've got with A and B here in Bayes' theorem, that this is like a joint distribution for both theta and x. I've got both of these guys together. So what needs to go in the denominator here? Well, what am I conditioning on? I'm saying I know x. And so this guy is, I can write it a couple different ways. I could write it f of x, but what you'll often see more often in Bayesian statistics is the following. So I said the numerator is kind of like the joint distribution of theta and x. So let's do p of theta f of x given theta again. But this should just be a distribution on x, right? Just like this is a probability on A, not a joint probability on both. And so how do I take this product, this thing like a joint probability, and turn it into a probability just on x? Well, I marginalize it. The marginal probability for x is what I get if I take this and I integrate out theta. And so this is sort of the core statement of the posterior distribution in Bayes' theorem. So I take my prior PDF, I take my data model PDF, so this is the likelihood again. I take the prior times the likelihood, multiply those guys up, divide by this thing down here, and then that gives me my posterior distribution. This is just pure math. There's nothing particularly hard going on here other than doing some arithmetic. But notice that this term down here, I'm integrating out theta, right? If I'm integrating out theta, then this term in the denominator is not a function of theta. So I can actually write something a little more interesting. If you don't know this symbol means proportionality. This means that I'm going to have this relationship up to a multiplicative constant. And that's what I'm saying down here. This guy is a multiplicative constant because it doesn't involve theta. So up to proportionality, I can say that this is p of theta times f of x given theta. And now I lose the nasty stuff in the denominator. Why can I get away with this? Well, this is a probability distribution, right? This guy I've got over here, this posterior distribution, it's a probability distribution. If it's a probability distribution, that means that there has to be a total probability of 1, which means that if I were to integrate the whole thing, then that integral would have to come out to be 1. This guy on the bottom here, this is just a normalizing constant. This is just a multiplicative constant. It's the constant that makes this go to 1. But it doesn't involve theta. The only thing that involves theta is the numerator. And because of that, I can say that the posterior is proportional to this. And then whatever's going on down here, I don't really need to worry about it. I just need to have the whole thing come out to be 1 in the end. This is going to lead us into what we're going to talk about in the next lecture, which is conjugacy. Conjugacy is sort of the easy version of doing Bayes, which is pretty much everything that we could do until about the mid-90s when computers improved and we could start doing Bayesian computation, which is sort of the big thing in statistics right now. It opens up your ability to do a lot of problems, but you need to have computers to do things for you because the math gets too hard if you get outside of a particular range of problems. But we can look at a couple of those problems. So we will talk about conjugacy in the next lecture.